Hello and welcome. This presentation is a paper review of a scientific paper called Mapping Flash Flood Severity in the United States. The presentation is by Megan Civic, although I am not one of the authors, and it's for the purposes of the University of Oklahoma course Hydrology, summer 2019. Here you can see the citation of the paper and the authors responsible. The outline of this presentation is as follows. We'll have the introduction, which will summarize the characteristics of a flash flood, why it's important to understand flash floods, and the purpose of this study. Next, we'll talk about the approach, which was to characterize available datasets to expand outside of gauged basins using parameters from continuous datasets. Then we'll follow and talk about the methods for that, determine the flashiness, monthly variability, and associate flashiness with geomorphology and climatology. Then finally, we'll talk about the conclusions of this study. This paper interested me. I live in Arizona, and it was designated as one of the flash flood hotspots, so it immediately got my attention. To expand on that, it's in the news every year. You can see some of the images in the news recently. This one was kind of interesting, where Phoenix has a lot of their highways actually dug down, which in a dry desert usually isn't a problem, but with a really high intensity quick rain, it flooded out the freeway. And then often we see images of cars trying to cross washes that are usually dry, but on flash floods they fill up. And then of course the hikers that get caught hiking down in the dry desert, but the mountain tops were getting rain and a flash flood can come. So what characterizes a flash flood? Well, from this paper, it demonstrated and discussed that a flash flood is related to localized short, high-intensity rainfalls over basins with short response times, that it's multidisciplinary in nature, controlled by optimum combination of high rainfall and basin physiographic and morphological characteristics, and it's difficult to forecast. Flash floods are a majority of floods which cost billions and lives. It presented the statistics for 1 year, but I thought it'd be interesting to look at the spatial distribution of flooding, which, since flash floods are a majority of floods that cost money, this is a good analogy, I feel. And it also shows kind of more of a long-term cost. The paper mentions that the majority of flood fatalities are in fact from flash floods. I went to the National Weather Service website to see the spatial distribution and magnitude of flash flood fatalities. I'd like you to notice that Texas often has a magnitude each year. You'll see sometimes each state has a high magnitude every now and then. What I'd also like you to see is that almost every state is shown to have at least one flash flood fatality during this time period. So we'll go through these slides, and I encourage you to look at your state in particular and to see how you're affected. 2010, 2011, 2012, 2013, 2014, 2015, 2016, 2017. Living in Arizona, this was a particularly sad year. A lot of hikers were caught in a slot canyon. And then finally, 2018. Another reason why it's important to understand flash floods. The paper mentions the frequency and impact of flash floods are expected to increase due to an increasing trend of heavy precipitation and rapid urbanization. Also, understanding can help with flood risk management and mitigation. To better understand how this study differs from previous studies, this slide shows previous studies summarized in the paper and how they try to understand flash floods in ungauged locations. First, they compiled an observational database of gauged locations. Other studies developed a flash flood index to distinguish between floods and flash floods based on the shape of the flood hydrograph. This helped establish some methods on how people determine when it's a flood and when it's a flash flood. Importantly, for this study, they determined the causative mechanisms such as basin morphology, flood-generating rainfall, peak discharge, runoff coefficient, and response time. The big difference between previous studies and this study is that the previous studies characterized by frequency, severity, seasonality, synoptic meteorological causes, and human impacts. This study is different in that it proposes a new variable to describe the severity of flash flooding for the United States, which they call flashiness, which identifies basins with a high conditional probability of having large magnitude discharge in a short period of time. It identifies hotspots and evaluates seasonality. It also uses the flashiness analysis in the gauged basins and extrapolates a continuous grid based on topography, hydroclimatology, underlying geology, and geomorphology. It identifies flash flood prone areas not highlighted in the observational database. The approach of this study was to look at snowmelt, intense rainfall, to understand the hydrograph, such as this, where we have a lot of precipitation, and then here's the streamflow hydrograph, saying the underlying basin dictates the speed in which water is conveyed and the magnitude of discharge. In this image below, you can see that, well, it was an urban area, so it really conveyed water and sediments being carried by the water. This study factors in available information from gauged locations, such as the Unified Flash Flood Database, and a variety of sources, such as gauge measurements of stream flow by the USGS, flash flooding reports from the National Weather Service, and public survey responses. The database was enhanced with geomorphologic and climatological attributes derived from each basin in the study. Those geomorphological parameters are included in this table, and they include things such as basin area, shape factor, river length, relief ratio, slope index, slope to outlet, basin curve number, K-factor, rock depth, and soil texture. Quite a few parameters. The study takes that information and utilizes it with DEMs to expand to ungauged locations. It derives geomorphological attributes from digital elevation models, or DEMs, for potential flash flood severity. It looks at soil datasets to determine mean depth to bedrock and erodibility. Land cover and land use datasets are used to estimate runoff curve number, and hydroclimatologic variables of mean annual precipitation and temperature from 30-year normal datasets are also used. And ultimately, they wanted to provide a continuous dataset through the whole U.S. to expand our knowledge of flash floods where we do have information to areas where there are no gauges to confirm. The methods of the study include determining the flashiness of a basin, determining the monthly variability of flash floods by region, associating flashiness with basin geomorphology and climatology, and the regionalization of flashiness. This study presents a new variable that previous studies haven't, called flashiness. It finds it as the difference between peak discharge and action stage discharge, normalized by the flooding rise time and basin area. The study had this equation, which factors in peak discharge, action stage discharge, basin area, and flooding rise time. You can see on the streamflow hydrograph how the slope determines the flashiness. In particular, this study identifies those basins with a high conditional probability of having a large magnitude discharge in a short period of time. The scaled flashiness variable is the median value computed from all flooding events observed at that station. The study presented this map, which shows the distribution of observed flashiness over the entire United States. It presented flash flood hotspots, which are highlighted in the boxes shown on the image. It's important to note that this study only assessed USGS gauged basins that have flood stage definitions. The hotspots included the West Coast, Arizona, the Front Range, Flash Flood Alley, Missouri Valley, and finally the Appalachians. The study provided the following descriptions for each of the hotspots. I thought it would be interesting to look at images to compare the hotspots. So for the West Coast, it's restricted to coastal basins and upslope region of the Sierra Nevadas near Lake Tahoe. There's a quick Google search of California flash floods. You can see a lot of mudslides characterize those flash floods. Meanwhile, in Arizona, flash floods typically happen in the southeastern part of the state and along the Mogollon Rim. Here is another example where flash flood came roaring down a mountain into a dry creek. If you're in that creek hiking, there's nowhere to go. Also, what you see a lot in the news is it really affects travel because this wash is usually dry. Usually it's not a problem, so we don't build bridges over it. The Front Range has several flashy basins to the east of the Rocky Mountains. In Texas, Flash Flood Alley focuses around San Antonio, Austin, and Waco along the Balcones Escarpment. In the Missouri Valley, you can see that the floods are very expansive. They're not limited as much to channels as the previous examples we were looking at. And finally, the Appalachians have high values of flashiness along the mountain range, from Georgia to Maine. The study also compares the monthly variability of each of those hotspots. So for the West Coast, the cool season phenomenon is related to the jet stream position, and it peaks in the winter months. Down in the right, you can see the time series and the number of flooding events. For Arizona, my home state, a reflection of the cool weather phenomenon from the West Coast is seen in the winter months. It also has a secondary peak in July-August from the North American monsoon transporting moisture from the Gulf of California. It has a bimodal character. The Front Range is related to large-scale circulation patterns with the North American monsoon from the Gulf of Mexico. The frequency increases at the beginning of the warm season. It peaks more in the summer. Flash Flood Valley in Texas is caused by a combination of climatic and geomorphological factors, such as the tropical air from the Gulf of Mexico, tropical cyclones, and the orographic uplift. It has a bimodal character. The valley is related to warm air from the Gulf of Mexico. It has a flash flood peak in the summer. Even though rainfall bimodal, intensity in autumn is not enough to cause flash floods. And lastly, the Appalachians. Warm air from the Gulf of Mexico and Atlantic are forced up the slopes of the Appalachians. Peak is in March and September. The study then associates flashiness with basin geomorphology and climatology. In the DEM, it analyzed the basin area. You have other colors, you have larger basin areas. It analyzed also the mean annual precipitation, slope index, finally the curve number. It then statistically analyzed the influence of each factor and showed this by quantile plots. Median shows the dependency, and the variability is shown by the quantiles. The study found that flashiness decreases as basin area increases. The quantiles show that there's still some variability. In the median, you can see that flashiness, the general increase, mean precipitation increases, but there's still quite a bit of variability. From this plot, you can see flashiness definitely has an increasing trend. The slope index increases. From the median, you can see flashiness has a slight decreasing trend as the curve number increases. Finally, all those methods previously mentioned are compiled into the regionalization of flashiness. It's a generalized additive model for location, scale, and shape to examine dependence between various explanatory variables, such as geomorphology and climatology, and flashiness. It assumes flashiness is a response variable. Its distribution function varies according to geomorphological variables. Flashiness is a random variable following parametric distribution. Here's the meat of the study. The model used to make predictions of flashiness across the United States. It potentially identifies flash flood hotspots in ungauged areas. Better understand the risks in areas where we don't have data. On the left, we have the distribution of expected flashiness values. So the warmer the color, the more expected it is to be flashy. Right, we have the standard deviation of the model. The study validated the model by correlating between the modeled and observed flashiness gauged locations, and you could see that it had a fairly good correlation, and it was fairly accurate. It also validated the model compared to the flash flood fatality map. The study presented the following conclusions. An extensive 78-year database was used to explore dependency of flood severity against geomorphological variables in climatology. Flashiness, a new variable presented by this study, shows a measure of flood severity as a potential of the basin to produce rapid and significant response to heavy rainfall. It really focuses on the basin and the climate data. 6 flash flood hotspots were identified across the country. Monthly analysis reveals very different behavior and seasonality in each region. Several variables were used to model flashiness, with basin area and slope index as the most influential. Ultimately, a continuous model was developed to make predictions of flashiness in ungauged areas to potentially identify flash flood hotspots. What I thought was most important was previous studies characterized flash floods from observations, causative factors, and were largely frequency-based. This study proposed a new variable, flashiness, which uses basin parameters from a DEM and continuous climatologic modeled data to expand from where we do have information. Ultimately, the study extends the gauged basin information to ungauged basins and provides a continuous map for the U.S. of areas where there is a high risk of flash floods.